Hi, everyone. Welcome to this lecture series, AGU Fellowship Lecture Series. I'm Julio Cañón, professor at the University of Antioquia School of Engineering, and I am very honored and pleased to have Dr. Claudia Tebaldi today with us. This is the third AGU Fellowship lecture that we host at the university, which is an honor for us to have here these lectures. And for even more to have Dr. Claudia with us today. She has been working on climate change science since the early 2000s. She is a statistician by training, and her work has centered around uncertainty characterization in future projections of climate change, with focus on changes at the regional scale, particularly in extremes. In the last decade, her work has shifted increasingly towards connecting the physical changes in the climate system to impact studies and risk assessment. She joined the Joint Global Change Research Institute, a division of the Pacific Northwest National Laboratory, affiliated to University of Maryland in 2019, after many years at the National Center for Atmospheric Research in Boulder, Colorado, and visiting positions in Stanford University and University of British Columbia, Vancouver. She has worked as an author on the last three assessment reports of the Intergovernmental Panel on Climate Change as part of the Working Group 1 on the physical science basis. She was an author of the fifth
Recording in
US
progress.
National Climate Assessment, released in 2023. She co-chairs Scenario MIP, which organizes the coordinated scenario simulations by the world's climate modeling centers under WCRP. She maintains an affiliation to Climate Central, a nonprofit, non-advocacy science communication organization dedicated to educating the US public to the impacts of climate change and its solutions. Dr. Tebaldi is an elected fellow of the American Geophysical Union. We are very pleased to have you here. Claudia, thank you for accepting this invitation to be part of this program. And we are eager to hear your presentation, your insights about your work, the ideas that you have for the future. These conferences are thought for new scientists, students at the universities, feel engaged with the science that AGU promotes around the world, and as well all the geophysical sciences. And we are very pleased to have you here. Thank you, Claudia, for being here with us.
Well, thank you. Thank you for the invitation. And I'm very honored to be talking to you today, and looking forward to give you what I hope is a broad enough picture of the type of work that I'm involved in that may have some pieces that are interesting for anybody in the audience, hopefully. So as you see from my title, I'm going to talk about integrated modeling of the Earth and human systems, and I'll try to tell you about past work, but also challenging aspect of this work, and hopefully give you some idea about future directions. So the way I want to do this is by starting with this graph. This graph is supposed to give you a sense of the main component of the problems and the type of models we use to connect these components to have a flow of information among these components. And I should say, some of you may be more interested in, the type of analysis and modeling at a very regional scale, very detailed, maybe a specific sector, a specific aspect of an ecosystem. My type of work has always been at a very global perspective and scale. So by necessity, if you will, fairly coarse in the representation of the various regions or the various sectors, but with the idea of giving a big picture sort of outlook on the problem. So, if we are concerned with global change, and we are concerned with the role of humans in affecting our environment, we start from considering those human activities that create either emissions of greenhouse gases or land use changes. That's what LUC stands for in the second box here. We usually represent this aspect of the problem with so-called integrated
They say that the sound wasn't coming through, but he's trying to check on the presentation. Okay, let's try it again. He's gonna check that everything is working. Go ahead.
So can
Can
the
you-
sound
Okay, can you confirm that?
can you hear me?
I can hear you very well in Zoom, but I am just checking that he's okay with the.
Yeah.
Yeah, he said that he's okay. Yeah. Go ahead.
Okay, so tell me if I should restart, or if I should go on where I was.
Maybe if you want to restart is fine. And I'm sorry, Claudia, for
No,
the
that's
inconvenience.
okay. That's okay. I rather have something that makes sense.
Okay, thank you.
Okay. I present this graph because it allows me to talk through the components of the problem that make up this, complex system that is made both of the natural system, the Earth system, and the human system. And so when we're concerned with modeling global change, the effects of human activities, we want to, first of all, hypothesize how future evolution of society and the economy is going to produce, future emissions, future changes in land use. We have integrated assessment models that allow us to model this step. These integrated assessment models are trying to represent the various sectors of the economy, the various aspects of the human system like society, population, education, urbanization, and then sectors like water sector, land sector, the energy sector, importantly. So once these models are guided through different hypotheses or alternative of future evolution, and I will talk about this in more detail, they can produce pathways of emissions, importantly, of greenhouse gases and other gases that affect our Earth, our climate, and changes in land use. If we want to translate those things, those emissions and land use changes into changes in climate, we need to first translate emissions into concentrations in the atmosphere, because that's what really affects the imbalance of energy that comes in from the sun and leaves the earth. That is called radiative forcing. So to translate emissions from our activity into concentrations, we need to have a sense of what the carbon cycle is doing. And traditionally, until a few years ago, the way we were modeling these steps was by using a simplified model of the carbon cycle. We called it a simple climate model. And once that simple climate model translated emissions into concentrations, we could then take those concentrations and feed them into our climate models. Climate models are very sophisticated representation of our climate system. They are very costly. They run on supercomputers, but they produce these beautifully complete representation of how the climate system evolves as a function of how much greenhouse gases we produce and remain in the atmosphere, how we change the surface of the earth by planting more trees or deforesting or putting land to agricultural cropping and things like that. Okay, climate models give us, temperature, precipitation, wind, humidity, anything we observe in our climate system, climate models can give us. But usually, when we're concerned about our activities and what they mean for the climate, it's because we are concerned about what those climate changes mean for the things we care about, right? So our health, for example, our infrastructure, our economy, our natural system, our natural environment. So we use those climate variables as they change in the future, as the climate models tell us, to run impacts models to tell us something about impacts and risk of climate change into the future. Now, if we want to do things right, we want to talk about impacts and risk, not only in terms of what changes in the climate, but also what changes in the future in this society and in the economy, because there are aspects of the human system that determine exposure and vulnerabilities to climate change that are important to consider when we want to consider and talk about impacts and risk. Now, I mentioned that this double step here of the simple climate models and the general circulation models was the way to do things until a few years ago. Because as models, climate models become more complex, they are actually including the carbon cycle. And they are including the carbon cycle in a way that all of a sudden allows us to represent feedbacks. One example of those feedbacks is, for example, the fact that as the climate warms, we may cause more wildfires that can, increase the amount of carbon dioxide and aerosols that are emitted. Or, as you have heard, I'm sure, many times, there is the concern that a warming climate will cause a melting of the permafrost in the Arctic, and with that, more methane will be released. So if we have a model that has the carbon cycle as part of the entire process, the entire system, these feedbacks can be represented. But now I'm going to put up a last arrow here, which is really what encapsulates what excites me the most and what is really, I think, the frontier of this modeling that I'm sure is becoming already very complicated under your eyes, but now I'm going to add another arrow, which is that represents socioeconomic feedbacks. So let's think of things like damages perpetrated by, extreme events, or let's think about the fact that labor productivity may change because the temperatures become so high that people cannot work outside anymore as productively, or maybe not at all. Um, these are the kind of feedbacks that will affect the economy, and an economy that doesn't grow as fast because of these damages or because of this change in labor productivity will change the amount of emissions, because emissions are really related to the size of the economy. The emissions are related to how we use our energy system, how we use our transportation system. And to a first order, the amount of emissions is very, very strongly related to how large the economy of a country is. So I hope now to go through a few of these steps. Hopefully there will be enough time to attach a little bit of meat to some of these modeling steps. I've been working on several of these, and so I'm using my experience to, first of all, talk about scenarios of emission and land use change, because I want to give you an idea of how we produce these scenarios that drive our climate models. I hope many of you have used at least climate model output, and you may be familiar to SSPs and RCPs that were the labels attached to the various scenarios. The high scenarios, the low scenario, the medium scenario usually had labels that would allow us to, to talk about these scenarios. So the last time around that the climate models got together, organized, and ran a simulation of the future was a project called CMIP 6. And CMIP 6 adopted a set of scenarios that were called the Shared Socioeconomic Pathways, SSPs. If you have used climate model output, I'm pretty sure you have heard this term SSP. And I want to give you a sense of how mainly social scientists, economists, demographers produce these scenarios. Because if you are a climate modeler, all you care about the scenario is how much greenhouse gas concentrations they represent in the atmosphere. But usually these scenarios have a very deep and strong logic to them. the scenarios start with narratives, qualitative description of broad patterns of development of the human component of the problem into the future, and they create these narratives in a way that all the elements have a logic that relates each other. And I'm going to give you an example or two very quickly. Once those narratives are developed that create these alternative futures for the human population and the human system, the economy, the societies, we develop quantitative elements that are consistent with those narratives. And those quantitative elements are things like, you know, how much population will grow and where it will be located, how education will develop into the future, how urbanization, and importantly, how the economy, the size of the economy will grow, how fast or how slow it will grow. GDP, gross domestic product, there is, a metric for the size of the economy. So I want to give you an example of two alternative scenarios that have been developed that are interesting because they paint a picture of the future that actually maybe we may find unfortunately a little familiar here. So one of them is called SSP3, called regional rivalry. And some points of the narratives are as follows. This is a future where the world will be, under in a situation that is similar to the Cold War, except it's a multi-pole Cold War. It's no longer two powers against one another, but there will be different powers around the world that will be in this state of conflict. And the state of conflict will make individual countries focus on security, put barriers to trade, to migration. Um, there will be little investment in health and education because resources will be put towards, these other priorities. And therefore, as a result, there will be slow technological progress, weak institution, slow income growth. An alternative scenario that was developed together with this one was called fossil fuel development. And these scenarios was hypothesizing a rise of the global middle class, rapid technological progress, large investment in human well-being, like health and education, well-functioning institutions, rapid economic growth, fossil-centered energy system. Um, I should say the last one should have given you, a little bit of a shock because everything else was very positive, but the assumption was that all these good things were relying on the continued exploitation of fossil fuels. So these are just narratives for now, but we can think of developing, as I said, things like projections of population growth or the education attainment or GDP growth that are consistent with these narratives. And I'm going to show you quickly a couple of countries because these things are developed at the country level usually, where under these two different SSPs, the regional rivalry in red or the fossil fuel in pink, here are trajectories of development of population for two countries. And you see here that under that regional rivalry scenarios, India continues to see a fairly sustained population growth, while under the SSP5, which is a scenario of rapid development, population actually starts to decline, which is the typical pattern of a country with strong economic development. For China, in both cases, there is a decline because we know that China is already on the declining branch of population growth or degrowth, but you see that the decline is much faster under the strongly developing scenarios, SSP5. The projections for GDP, as you can imagine, see a very strong growth of GDP for both countries under SSP5 and not as much under SSP3. Now, why am I showing you all these? Is because these are ingredients that go into so-called integrated assessment models, that are these models of the various sector, energy, water, land, socioeconomics, that take all this information and then project into the future what is going to happen in terms of economic activities and, of course, as a consequence, emissions. And so when you do that for all these SSPs, and we had 5 of them, you create alternative futures in terms of emissions. And these will be the alternative scenarios that will guide the simulations of climate models. So here in this picture to the right, I'm showing you CO2 emissions for many trajectories. Let's focus just on the colored one that belong to the various alternative SSPs, 2 of which I've presented to you, SSP5, the fossil fueled future, and SSP3, the future that is, characterized by a lot of conflict and slower economic growth. And you see that if you run these scenarios from integrated assessment models and derive these emission, of course, you get much high emissions for SSP5 and somewhat lower emission for SSP3. Now, the game that you can play also with the integrated assessment model is to impose some mitigation policies. So you can, for example, impose a price for carbon so that the model evolves by also accounting for the fact that now all of a sudden burning fossil fuel is going to be costly. So maybe you will develop more, renewable sources, for example. And this is what happened when we develop so-called mitigation scenarios. You see here that for these other scenarios, the emissions after a while start declining. And these are futures where by imposing mitigation policies, society decides to curb their emissions. And interestingly, you can see there is a trajectory here that is called SSP5 as well. So this trajectory is developed based on the same narrative that we just looked at that produced this high scenario. But now in the model, you can play with mitigation action, and so much so that the scenarios can become much lower and very different from what you obtain by not considering any mitigation. Okay, so we are at the point, I hope, where we have a sense of how alternative emission pathways are developed by integrated assessment model. Now we can make another step and look at Earth system models, what they produce on the basis of those scenarios. This is actually the part of the problem where I spent most of my career before starting to be more concerned about impacts and mitigation scenarios. But so here we are with our alternative future emission pathways all the way to 2100. And we are going to feed them into Earth system models thanks to this project that I mentioned. It's called the Coupled Model Intercomparison Project, CMIP. It organizes these type of simulations by gathering all climate modeling centers around the world that want to participate and produce climate projections that can be comparable because they are using the same scenarios. That's an important part of, characterizing the uncertainty of climate projections because different models have different responses. So just as a curiosity, where are these climate modeling centers located around the world? You see that mostly they belong to Europe and North America. China is becoming a big player in the climate modeling world. There is a climate modeling center in India, one in Brazil, and one in Australia. But we need to diversify this a little better. So here are projections of temperature and precipitation averaged at the global scale from 5 different scenarios. So 5 of those different colored emission pathways that I presented before. And I want to just point out that here you see a thick line, but you also see a very large envelope around each thick line. This is the uncertainty that I just was talking about. Different climate models respond more or less strongly to the same concentrations in the atmosphere. So we need actually to have all these models to get a sense of the uncertainties when we project climate into the future. So you see that here you have a scenario that SSP5, the fossil fuel scenario, that produces a very strong warming, both in terms of the ensemble mean, but also in terms of course, the upper reaches of the uncertainty cone. And you have scenarios that are much lower. So these were scenarios that were actually developed to meet the Paris Agreement targets of 1.5 and 2. So you see that these scenarios are actually getting to 1.5 and 2 by the end of the century, at least in terms of the mean response of our climate models. We also see that precipitation, when globally averaged, follows the same behavior as temperature. And we know that that is the case because there is a very direct link between warming and wetting of our planet. But you see here also a lot of uncertainty. You see, for example, that the scenarios don't really diverge until the middle of the century for a quantity like precipitation. So besides, the effect of our actions on the climate, we also have to reconcile with a lot of variability in the system that would be there even if we were not affecting the climate, but perhaps gets affected itself, variability gets affected itself by climate change. Those are interesting questions that climate scientists grapple with all the time. But of course, nobody cares about global averages. And so, except if you are, concerned with policy, and so those kind of experiments can give you a sense of when you would reach those targets under the different scenarios. But let me skip this and go to some more interesting maps. So as I was mentioning, nobody really cares about global averages, especially for precipitation. These are actually just snapshots of changes by the end of the century under those 5 different scenarios. And, we can focus on our regions of interest. But what I wanted to actually say here at a more global scale is that, and maybe this is more obvious for precipitation, but it's very true also for temperature, the pattern itself, the relative, wetting or drying, the relatively warmer places or cooler places remain the same across these scenarios. What changes is the overall intensity of this pattern. So this is actually a characteristic of our projections that has been robust for many years, if not decades. And it's an interesting aspect of the global climate system, at least at this scale, of this very coarse and kind of um, um, 10,000 meter type of view, that the places where things are happening don't shift around. So we have known for a long time that the high latitudes are going to warm more than the low latitude, that land is going to warm more than the ocean. We have known for a long time that the high latitude are going to become wetter, that certain areas of the world are going to become much drier, and those haven't changed. What changes here is the degree to which these things are going to happen, and that degree is actually proportional to global average temperature change. So much so that scientists like to talk about patterns that are changes per degree of global warming. So here is a map that doesn't have a name for a scenario anymore. So after spending all this time talking to you about scenario, now I'm completely sweeping them under the rug. And I'm talking to you now only as temperature change per degree of global warming. So here is a map that tells you that actually, Colombia here seems to be warming more or less in in pace at the same pace as the globe, while there are areas here in the Arctic where the pace is much higher. It's at least twice as fast. So if the globe warms by 1 degree, we expect this region to warm by 2 and possibly more degrees. Um, and this is a fairly stable pattern of change across scenarios and even across time. Um, amidst the noise of variability that we were talking about. And the same is true for precipitation. So precipitation here, um, as I mentioned before, high latitude wetting, the Mediterranean, the Amazon, part of Australia and South Africa drying. And the change here again is a percent change per degree of global warming. So if the globe warms by, 4 degrees, you have to multiply these changes by 4, and you'll get a sense of what to expect. Okay, and you can play this game with many other quantities, maybe more interesting quantities that like temperature during the hottest day of the year, or precipitation during the wettest day of the year, or soil moisture change. There is this general, behavior that says where things are happening remains fairly constant. What changes is how much is happening, and that how much is proportional to global temperature change. Okay, now let's try to address for a moment the impact side of things. So I mentioned at the very beginning that when we want to talk about impacts and risk, we cannot just consider how climate is going to change, but we have to consider how other aspects of the problem are going to change into the future. And those aspects are related more to the human side of the problem. So exposure, how many people, how many structures are going to be in harm's way when the hurricane hits or when the flood comes. How vulnerable will those things or people be? What will be the general economic standing of that area that is affected by these hazards? What will be the capacity of the government at every level, any level, to respond? So these are all determinants of the problem that we cannot forget about, because the same type of change in the strength of a hurricane will mean very different things if that hurricane hits, a rich and resilient place, or it hits a poor and, already challenged place. So this is what I just said. I'll just add that we use models to project ahead how, as I mentioned before, how many more people will be in that place, what will be the economy, and of course nobody is so arrogant to think that these are predictions of the future. These are projections. That is, we try to span a range of alternatives that gives a good sense of how different things may be, so that we can test our understanding of what the risk will be according to this alternative. But of course, everything we do is fraught with uncertainties and variability. I always say I'm a statistician. The reason I've had my job for all these years is because there is no end to, the need for characterizing these uncertainties, quantifying them, and putting boundaries around our answers. And so, Julio, you should tell me for how long I should talk. By my measure, I would have another 10 minutes, but I don't know if it's too long now that we lost a little bit at the beginning.
Yes, don't worry. You can add more time. It's okay.
Okay, thank you. So uh, I want to just mention what are the challenges that affect most our ability to characterize risk and to studies impacts of climate change. Um, so first of all, everything that I talked about, you can think of it at a very coarse and large scale, like I was presenting it, but you can think of it as, something that happens at a very local, very specific case. And so, of course, is the type of work that we do for impacts. The scope of what we study can be very different if we are interested in saying something about, global impacts of climate change, or if we are focusing on a very specific region, local, population sector. And the kind of economic models that we use to, for example, try to put a cost on the impacts of climate change can be very simple, very aggregated, or can be very detailed. The methods we use go from econometrics and statistical analysis to models that actually model the processes that affect things. So, we have hydrological models that help us model floods, and we have models of what exists along a coastline to measure the impacts of that flood on those structures and infrastructure. When we talk about impacts, things can happen in very different ways at very different scales. And then it becomes very difficult to try and summarize things. So there is a whole area of research that tries to aggregate the cost of climate change to say something about, for example, how much we should price carbon. And this is just a representation of a meta-analysis where people have collected the answer to the question of how costly is climate at 1, 2, 3, 4 degrees is going to be, from different studies, from very different studies that use, as I was mentioning, different scales, different models, different levels of aggregation. And you see here that there is an enormous range of answers to the question. So there are studies there is actually one study that says that 1 degree of warming is going to be beneficial. You see the y-axis says percentage loss, and we have a negative number. So this is a study that says warming is going to perhaps, make, I don't know, the economies of the northern region better, more things to grow, for example, that kind of thing. And there are studies that for the same level of warming say that already we should experience 10% of loss of global GDP. So, and as you go up in warming, you see these very, very large differences. So here, this is a lot of what people, are concerned about, trying to quantify and try to understand why different models tell us different things. And I hope I gave you a sense of how difficult doing that is. Yeah, this was just a line to show how large the uncertainty is as we go up in warming. Um, we also have difficulty in addressing different type of impacts. So there is a lot of work that has related, for example, mortality to temperature changes, changes in labor productivity to, for example, heat stress, crop productivity to changes in both temperature, precipitation, energy consumption, of course, as a function of warming, coastal infrastructure that is hit by things like storm surges or just sea level rise in general. There are a lot of other things that we call impacts that are either much less studied, and you see here a long list, or that are even altogether missing because we either don't have the models to do that, we cannot put a price on things, or the dynamics that lead to some of these things are so complex that climate change all of a sudden is just, you know, additional stressor, and we cannot really quantify by how much things are going to change because of climate change. Things like, you know, crime and conflict, mass migration, and tipping points. Tipping points has been a very much studied topic, but for example, our climate models don't show us obvious tipping points in the system, and we don't know if it is because climate models simply cannot represent these you know, critical cliff edges, or if it is because the system is as resilient as they seem to think. There is an interesting article here about this, if you are interested in reading more. So just to finish all this, I want to talk for a moment about this idea of integrating everything, modeling everything, everything represented and you know, connected to the various components of this problem. And I go back to this schematic only to say that, you know, I think I presented to you some of these links, definitely how models go from representing human activities to creating these pathways of emissions, how climate models are going from emissions or concentration to changes in climate, and how we more or less, better or worse, we can represent impacts. What is still work in progress, and definitely what drives the work that I'm trying to do right now, is this idea of putting everything together and representing these feedbacks, and in particular, given how difficult it is to represent these impacts, to model these feedbacks from impacts to the economy, from economy to emissions, from emissions to climate, and all around again. So, you know, if you are a climate modeler, that your focus is the climate system in itself, the physical climate system, you are trying right now these days to put an integrated assessment model that represent the human activities into your climate model. This has advantages because climate models have this very detailed representation of processes. So they can give justice to a lot of these interactions. For example, you can represent, you know, the need for irrigation because climate is changing, the need for more energy to cool our houses, our cities, and have everything in the loop. But these models are very, very complex. And when you add components like this, you become more challenging, representing all those uncertainties that I also mentioned, that affect as much, you know, our climate modeling than our impact modeling. So it's not just that impact models are very uncertain. We still have very large uncertainties in climate modeling. So the other option is to take the point of view of an integrated assessment model of the human system and now try to represent better the climate component. So you may have noticed it even before at the beginning when I put up this figure. If this is my integrated assessment model, one of the components should be climate so that we can represent both how emissions and other aspects of our activities like land use affect climate, but also how climate affects everything else, like our need for water, our need for energy, how much food we can produce. So that is what we are working on right now, this idea of representing climate in a model that is by construction a relatively simpler model than a climate model. So these integrated assessment models can actually run on your laptop. So you don't want to represent climate in a way that makes them too complicated. So we have a lot of work now going on where we build emulators using machine learning and statistical approaches to represent the Earth system in a more efficient and computationally agile way. And that's where our focus is going. So my summary finally, so I'm hoping to have given you necessarily shallow but fairly broad view of the problem of modeling global change, and to have convinced you that to do it right, you have to involve both the human and the Earth systems co-evolution, interaction, feedbacks. I think you can make a career by focusing on any of the individual pieces, but an even greater challenge comes from the need of modeling the whole system and trying to be this, multidisciplinary or interdisciplinary type of actor in the research community. And to do so in a way that is still manageable and interpretable, that allows you to test for uncertainties and variability. And only by doing that, I think we can answer the very challenging questions that the problem of global change poses to us as a society, as humans. And so, I hope many of you will be excited to join the challenge if you're not already working on it. So thank you for your attention.
Thank you, Claudia, for your presentation and your insights about your work and the history, because you are part of this history. You are part of the history of the process, and it's showing us, for example, the evolution of the ideas. I think from the beginning, the idea was, okay, we have to combine these two realms of the climate modeling with the human interactions. But obviously, the difficulties were high at the beginning. Now we are getting better at modeling or trying to model both together. And you showed us how, at least from the perspective of the big models, these scenarios, this way of thinking of future possibilities for humankind on the different tracks will put us in different situations, and we can try to, as you mentioned, predict things that can happen, and we can act in consequence, maybe with some time still to correct the path if there is that term, or maybe to improve the way we are adapting or ameliorating the impacts. So I think I want to open a space for questions from people, the people that the audience that is in our channel, the YouTube channel. If you want to write questions in the prompt, in the chat, you can do it, and I will try to read them to Claudia. Also, we have some invited colleagues here in the Zoom session. They can also open their microphones and their video if they want to share and ask some questions to Claudia about the topics. So I want to start just to break the ice on this moment and ask you the question. at the beginning, before we started, you were saying, okay, I work in big models. We here are more into local scale or scaling, downscaling the processes for local problems or issues. And I think you were kind of worried about that. It's like, okay, I hope it's going to be interesting for you guys, but obviously for us it's very important because many of our projections are based on this modeling,
Sure.
and we also noticed the importance of having a good answer for local communities that have to invest or decide to invest the scarce resources that they have, maybe to protect coastal areas that are going to be flooded. How you mentioned uncertainties, we still have some uncertainties on how this would happen, on how fast it will happen. So we have to maybe inform policymakers, mayors, people that are elected within a framework of 4 years with a lot of problems in their actions. But we have to tell them, okay, this is going to happen. The uncertainty exists, but you have to take a decision of moving the whole town inland, or just basically start migrating to main cities inland, because most of these coastal areas are going to be underwater, maybe in 20, 30 years time. But still, for us, it's very difficult and challenging to try to tell that as researchers to people.
Mm-hmm.
So the question that I will ask you is in terms of there is something called the maladaptation. Let's say, for example, if short-term fixes can worsen long-term vulnerability, let's say, or something like this.
Yeah.
But we have to inform people and decide in the action. How can we work on the uncertainties that come from the big models as well, and from the uncertainties that are from the local aspects, let's say? Can we improve that part of the agreement between those uncertainties to improve also the way we connect with policymakers and people in general?
Yeah. Yeah. So, I always joke about the fact that by staying at these very global scales, I avoid all the problems that actually people that matter, like you, that have to inform people, have to reckon with, right? Because you're faced with the reality of having to make a decision, and so I don't have a lot of experience. I do know that I think the successful examples always involve starting to talk about the problem with the people that are affected and need to make the decision at the very beginning, and try to formulate the question together from the beginning, so that your answer is not just a top-down,
Mhm.
release of scientific knowledge, but tries to address both the needs, but also the limitations, like you were saying, of having limited resources, or having to make a decision now that by construction is not going to be the optimal one, because we may not have all the information right now. So I don't have an answer, of course. If I had, I would have probably, I would be much more famous than I am. But I do think this idea of co-production of knowledge and solutions, it's really important to define the problem, to define the vulnerabilities, and perhaps to find out that the once you formulate the coordinates of the problem, maybe some of the uncertainties don't matter anymore, because they become orthogonal to the problem. So, but that's only by working with the people that are invested and affected, that you find that out. If this makes any sense.
Yes, thank you.
But I do think that the community is always trying, right, to either through modeling or through corrections to modeling. Now with machine learning, tries to make our projections better, more robust. So there is some progress in that direction, but I don't think we will be ever in a world without uncertainty. So we need to figure out how to work with it.
Thank you. Thank you, Claudia. We have Naylor. I don't know, Professor Naylor. I don't know who is in Diálogo de Saberes. Naylor, go ahead.
Hi, Julio. Dr. Tebaldi, thank you so much for your inspiring presentation. It was a pleasure to hear you talking. As Julio mentioned, I'm also a lecturer here at the university in the Faculty of Engineering. And my background is more in the disaster risk management. So I was working on my PhD on adaptive disaster risk management strategies. And I did some modeling of agents, agent-based model to include the impact of evacuation and lowering risk or not. But that's not what I want to ask you. I didn't ask Julio how much time do I have for questions, so I just speak to, let's say, more open question, because I fully agree that the way that we will be supposing to model is by integrating models. So I will not refute that. I completely agree with you in that part of your presentation. But based on your, let's say, distinguished career integrating Earth and human system models, I would like to ask you if you could share some pivotal moments or challenges that have shaped your interdisciplinary approach. Can you give these engineers that we are forming in the university, that normally we are based only on the hard science part, in the number, in the calibration of models, what can you offer? What kind of lessons can you share to emerging researchers for they to transition for these hard models to more integrated kind of modeling? That would be my first question. And I will ask you the second one, so you can be prepared for that, and I will go more on the models you show us today. Okay. And it's more personal. Sorry. Okay. My question is, do you believe that based on current observational data and model projections that we already surpassed the 1.5 degrees threshold? And if so, do you think that now we should shift more to adaptation strategies and stop talking about mitigation strategies? That would be my two questions for you. And thank you again, Dr. Tebaldi, for the presentation.
No, thank you for your attention and your questions. You know, I wish I had some lessons that were very exemplar, but my career has been always shaped by being in environments where colleagues belong to different disciplines. And you know, for the longest time, I was at NCAR, which is the National Center for Atmospheric Research. And traditionally, that was, you know, like the realm of physical climate scientists, physicists, atmospheric scientists. But I got there thanks to a little program that inserted PhDs in statistics into that environment, with the idea that they would work together with climate or atmospheric scientists. And that was my first experience of actually working with scientists from other disciplines, and I really started to love that. And then over the years, my career was also shaped by the fact that for a while at NCAR, they had formed a group that did integrated assessment modeling and was trying to do exactly this type of integrations, you know, 10 years ago, maybe even a little more than that. And having spent those previous year working strictly with physical climate scientists, all of a sudden this new perspective was open about the importance of the human component, right? Because if you are on the physical climate science, you tend to think that really what matters is what happens to the climate. It's only when you start talking about these things with people that study other things that your mind opens up. So the only lesson I can communicate is the idea of keeping as much as possible an open mind and seek colleagues that belong to other fields and that are willing to spend time finding a common language and trying to develop together, either strictly by working together on projects or just by talking together, because I feel like the perspective of people doing things differently from you is really important. And so after saying that, your question about 1.5. So I mean, if you're asking if we're gonna stay under 1.5, I don't think we will, right? We would have to vacate Earth tomorrow and move to the moon and until we find a way to mitigate. But I also think that adaptation is always a need. Like, we needed adaptation even at 1.1. So I don't think it's an either or. I think we should consider the problem in its entirety and try to adapt and most importantly to support and foster development in a sustainable way, so that as we develop as countries and society and we become more resilient, we also don't as much as possible add to the problem. But I feel like it's it's a trade-off in the sense that we should we should go beyond considering it a trade-off. I think we should it's not either or, either development or climate change mitigation. It's finding a way that slows things down while we foster development without imperiling it. So that's my view, my personal view. I don't say this as a scientist of this or that organization, but yeah. And in terms of if we are already at 1.5, I don't know, but it doesn't really matter to me. I mean, this 1.5 is a device, right, to talk about it. I don't believe it's a cliff edge. I think 1.6 or 1.4 could be as important. So yeah.
Yes, thank you, Professor Tebaldi. Yeah, I was more looking for your personal opinion,
Yes,
not the
yes.
institution academy.
Sure.
You have been working on that topic for so long. No, thank you so much, Dr. Tebaldi.
Thank you. We have someone called Diálogo de Saberes. I don't know who the person is, but if you want to ask a question, please. The person who is connected with Diálogo de Saberes here in the Zoom session. Well, okay. In the meantime, as well, another question. This is from the presentation that you made at the beginning with the scenario analysis that you projected, two of them as an example.
Yes.
Extremes. You said these are two extremes that we have, which are, when you think of them, one of them is just well-being with fossil fuels, which is contradictory with the idea of, okay, this is what is driving us to this point, but nonetheless is for the well-being of people. And the other one is the Cold War scenario with several multipolar world But what we are seeing right now, for example, in this situation that we're living, I think it's a combination of both, kind of a combination of both. You know, you see multipolar geopolitical movements in many places with stopping migration processes, but a lot of developing with more well-being for people in general, with using of fossil fuels that is increasing anyway. So in this kind of situation, when you see, okay, this is what so far is showing the direction for the next couple of years or 4 years, or we don't know exactly how long. How this combination of situations would change the work with the models. When you say, okay, it's not this scenario, it's not that scenario, it's the combination of both going together.
Right, right. Yeah, so as I was saying, you know, these scenarios are not hoping or trying to predict what actually happens, but to span a range of possibilities that kind of covers us. So of course I didn't present SSP1, which is a beautifully, you know, sustainable world with still economic development, but a more distributed, equitable type of society, and a lot of attention and concern for clean environment and quality of living and things like that. So that's a very extreme future in one sense, and then these two are extreme in another. There is one that is actually more like a middle of the road. I think it's actually the name of the scenario, that is kind of more of like a neutral continuation of current trends, thinking of current 2013, 14, when these were starting to be developed. So I think you know that the idea is that there is no, well, the other thing I should say is that no matter what scenario you're using, unless you apply a lot of mitigation from the very beginning, the emission pathways are not going to be very different for the next 10 years or so. And then they will start to diverge. So no matter what scenario you're using, the next 10 years are going to be what you imagine they can be, you know, just by extrapolation of current trends, unless you are really, you know, cranking down because you want to stay below 1.5. And so you're assuming things like everybody becomes vegetarian, you know, and we are going to electrify everything in the next few years. And so things that are not impossible, but are very unlikely to happen.
Thank you. Questions from participants? Apparently the chat in YouTube is closed, so people are not able to.
Oh,
but
no.
anyways,
Okay.
you feel free. We have some couple minutes extra. You want to ask another question? I think there is an ambulance right now passing by. So sorry.
No, we cannot hear.
There is another thing that is I want to ask you about, just the global modeling. Recently, we have heard this news about some studies that show, for example, that if the ocean currents change, some predictable results from this warming on the waters, there would be a possibility of a small ice age to the north that would affect maybe Europe a little bit and parts of North America. Which it's interesting because that maybe talk about the complexity of the models that are able to show these kinds of feedbacks in the climate system. This is not related to any human interaction, but just the climate. And at the same time, sending a message that is going to be being precise and maybe possible that's going to happen. The result is maybe something that will confuse people, because I think part of the unfortunately, I would say, the part of the myth that is created about this is just everything is going to warm up, everything is going to be just going into a steady state of warming. It's very difficult to get into the extremes, although even we experience them every year, and every year more and more with the statistics. But the statistics apparently don't affect much of what people in the cities think of the process. And on top of this, maybe processes that are going to be really going into the opposite direction. For example, a little reduction of temperature would produce even more difficulties for people to understand the impacts of changing the whole structure of the planet. So how do you see these situations, and how can we as scientists try to improve the way we communicate and tell people this is part of what we are doing and this is part of what the models are showing? Maybe they are improving the way we are detailing the processes inside, and they are showing us things that would be totally different than we expect from this warming. So how do you have you thought about that, these kind of situations for communication of science? Let's say this is more into that part of.
Right. So I feel the only thing I can say is that I feel like sometimes as scientists we cut corners in the communication arena. Like we tend to simplify things and for the sake of communication, and then we get into these issues of all of a sudden having to explain something that doesn't belong to the narrative. So I always try when I talk about things not to proclaim sweeping truths, because for one thing I don't have them, and for another I think like you are suggesting, things are complex, and there is so much that we don't know. So I feel like a little bit more of humility, and sometimes giving up the possibility of making a big statement, cognizant of the limits of what we know and don't know. I think it's an important thing for a scientist to remember. At least that's how I feel when I talk. So yeah, I don't know if I answered you, but that's the only thing I can say.
Thank you. No, thank you, Claudia. Questions, people? Okay, there is a question that obviously for the moment, I'm going to ask two things very concrete, because one of the colleagues that is not today here with us, she mentioned this to me. She was part of the IPCC report, the last report. She's one of our professors here. We are very honored also to have her here at the school. Is called Paula Arias. I don't know if you have heard of her.
Yes, of course.
Yes. So talking to her the other day she excuses herself because she couldn't be here today. But she mentioned that one of the things that we are trying to make possible is to have more data on regions where still the models are not very good at predicting or making good calibrations with real data. So most of the tropics or near regions where data usually are not very well represented. Is there, do you think that would improve part of these processes in the future for the modelers to include more information? How long that would it take to improve that part of making
I think there are some very promising examples where people are trying now to calibrate or refine the parameterization of models based on observations, and it's becoming part of the whole model development from the very beginning, the use of observations in every possible aspect. So I think what you're suggesting is indeed going to be really critical, and there is some work going on, for example, with a project based at JPL in Pasadena, where they are developing a whole new model, a climate model from scratch. And one of the characteristics is that of including, observations, not because we want to anchor the model to observation, because we can learn from observation to make the model better in terms of its process representation, its parameters and stuff. So I think it's going to be really important and actually critical, because there is this push, for example, for high resolution of models that are supposed to resolve all problems, because if you push the resolution, you can all of a sudden represent, processes like the convection that cannot be represented by coarser models, and that will take away a lot of the uncertainties in our projections. But to validate these models at this high resolution over the entire globe, you need observations, and you don't often have enough of those. So until we don't have good observations all over the world, I think this idea of resolving everything by having high resolution model is not exactly a robust a robust plan. Yeah, and I use, as a statistician, I used to be a little bit skeptical of these machine learning things, because as a statistician, you always think, oh, those are black boxes. While I'm a statistician, I can write down the model. But I'm a totally convert now, because they are so powerful. And as long as you are cognizant of the fact that they may be over parameterized and they can fit the data a little too well, they are really, really promising for a lot of problems. So
that was what was the next question I will ask? I was about to ask you was about exactly
machine learning. Yeah. I feel like it's really the frontier, and yeah, and we statisticians are part of history. but it's very promising, and there are so many good people working on it. So
good to know. And I think this is another message for people that still we have a future with a little time. I don't know how long, but a future with.
Let's try to be optimistic.
Yes, trying on the optimistic side.
Yes.
Well, this is. I mean, I'm gonna ask you the last question. I don't want to close this without asking this for you. And you, as mentioned before we started, you can call the Fifth Amendment if you want.
Yes.
I will try to put it in a way that is easier. It's easier in the situation that we are right now, but easier to answer. One thing that we expect from the advice coming from models and everything is at least to have a perception of what would happen. But apparently, politics in this moment is taking apparently the wrong steps. It's going in the direction that we didn't hope or expect to go, if things will be better or fixed or at least controlled in the near future. So we see, for example, the IPCC meeting that is going on this week or next week is going to have a big. I mean, all the commission from the US is not going to be present. We see. I mean, this is going to be a political statement for many years that is going to weaken not only the political sides and commitments, but also the science behind this, because obviously the report on the people depends on funding from big agencies to keep these possibilities of doing research. But politics seems to be going into the opposite direction, at least in the forthcoming years. How do you experience these days in particular? Because I know this is changing every day, but how do you experience the situations? What would be the consequences, speaking of scenarios, of having this kind of policies in our process of understanding, learning, and improving science on climate change?
Yeah, I just feel that a lot of it is really going against just the natural progress of things. so I'm hoping that there would be a natural correction of some of these charted courses in terms of, technologies and adoption of clean technologies, which is already happening. So we would have to have a real reversal of trends, right, to abide to the directions that are put forward. So But then in terms of the science, you know, I really, yes, I am worried because of exactly what you say, that the lack of funding and the lack of support is going to make a difference for years to come. And I am mostly sad and worried about the people in the field that are younger than I am. I have the luck that I've had my career already. It has been a very good career. I'm very grateful for that. And I cannot imagine being, you know, in the middle or at the beginning of my career in this situation and having to find my way with these challenges. So I'm very concerned about that, and I'm hoping that that rationality will prevail. I mean, science is what makes our life better in all fields, right? I'm not even talking about climate change in particular. It's just one. So I don't know. I'm hoping. I don't know what else to say.
Thank you, Claudia. No, I think it's a feeling for many of us, even for us that are not directly affected with that impact so far. So we are going to notice that.
And I want also to add that, you know, there is a difference between being a scientist and being an advocate. And I feel like sometimes that difference has been blurred, and it has not been a good thing. I think that, you know, as scientists, I feel like I've always tried to be, you know, to represent what I learned in an honest and multifaceted way, and recognizing the limitation of what I was talking about and what I was writing about. And so I feel like, you know, I hope that the people that ultimately have to make these decisions about life or death of the scientist will recognize that there is a way to do it, that most of us do, that is true to the science, and then there are some that decide to be, you know, more like the crusaders that maybe we need, but cannot be, you know, the emblem of the entire category of scientists. So
Thank you, Claudia. Okay, I think time, we are around 4:30 already. Thank you, the ones that were connected today and the ones in the future that will see this presentation in the YouTube channel. Hopefully we're going to have many visits and many students coming and seeing this presentation. We're sure we're going to try to publicize it in the school and to our colleagues. Thank you, Claudia, for being here with us again.
My pleasure. Thank you for your time and attention. I hope to visit Colombia sometime.
Great. No, you have a house here in the university, so we'll be in contact. And if you want, that would be great. We have a great group of a team of professors that are working on these areas that are really good at it, and they would benefit from having these contacts. And for sure, for us, it's going to be great. And I think this is the purpose. This is the purpose of this AGU.
We should thank the AGU for organizing this, because it's a wonderful experience for me, and yeah.
Thank you, AGU. And it's an honor for us again. This is the third time. I didn't expect to have the opportunity to have it for the third time, so we are going to apply for the fourth, and hopefully we're going to have. We're not going to stop now. It's just part of our deal. So thank you again. Thank you everyone for being here.
And hopefully sometime it will be one of you as the AGU fellow.
Hopefully so. Hopefully so. Thank you. That would be great. That would be great. And well, with this, thank you everyone, and see you next time.
Bye. Bye everybody.
Bye-bye.